Hi, in this lecture I will be going over another t-test. So we've talked about the single sample t-tests, the dependent samples t-tests, and now we're going to discuss independent samples t-tests. Okay, so we'll start with when we would use a t-test for independent means. Well, this is a test that allows us to compare two different groups. So for example, this test is most often used when we have two experimental conditions, such as a group that's getting some treatment or intervention and one group of people in our study that doesn't get the treatment. They're usually called the control group. Each one of those groups corresponds to a population in the real world. There's the population of individuals who are receiving treatment and the population of individuals who are not receiving treatment. And we want to know, typically, if there's a difference in those two populations on some underlying measure, like maybe disease symptomology. So if we want to know if those two populations are different, we can use a t-test for independent means to see if the means of those populations are distinct based on what we learn from the two groups in our research study. So the scores from those two groups are independent because they are obtained from different groups of participants. And that's important because it is dissimilar from the dependent samples t-test where you have two scores from the same individual. This will affect the steps in hypothesis testing because, of course, it will change how we define our populations in step 1. Population 1's mean will be generalized from group 1, and population 2 will be generalized from group 2. So we have two different groups of people. Both population means are generalized from sample means. So we have two different samples. Each one of those samples contributes to a population mean or mu. So now this allows us to ask the questions, how did the two population means compare to one another? So then the way that we state our hypotheses is also slightly different. The research hypothesis here for a two-tailed test is that the two means are not the same. The mean for the first population is different than the mean of the second population. And the null hypothesis for a two-tailed test, which is pretty typical for these tests, is that the two populations have equal means. Population 1 and population 2 have means that are the same. Let's take a moment to stop and think about what our goal is with this test. We are interested in drawing inferences about the difference between two different population means. So I want to just reiterate that the point here that we're interested in is a difference between means. So what would our comparison distribution be if we are interested in the difference between means? It seems like when we were interested in evaluating scores, then we used a distribution of scores as the comparison distribution. When we were interested in evaluating a sample mean, then we built a comparison distribution of sample means. When we were interested in difference scores or mean difference scores, then our comparison distribution was a distribution of mean difference scores. So now our unit of interest is our difference between two means. So our comparison distribution should be a distribution of differences between means. How could we construct that? Well, theoretically, what we're talking about is a distribution that's made up from sampling into population 1, sampling into population 2, getting a sample mean here, a sample mean here, and then calculating the difference between those sample means and saving it. So I'm only saving the difference, mean 1 minus mean 2, from population 1 and population 2. I'm saving the difference between those means for my comparison distribution. And I could do that over and over and over again. I reach into population 1, into population 2, get sample means, calculate the difference between those means, and I save it over here. I do that iteratively, over and over and over, and I start to construct a distribution that's made up of all differences between sample means. This is called the distribution of differences between means, and it is the comparison distribution for an independent samples t-test when we walk through the steps of hypothesis testing. So I know that that's a little bit abstract, so let's just take a second to visualize what I said. And there's a visual here from the textbook. So we randomly select samples from each of the two populations. And we calculate sample means from every time we sample to build a distribution of means. You are already familiar with this step. So we have the distribution of means for population 1, the distribution of means for population 2, and then I could reach into here and reach into here and grab two different sample means, calculate the difference between those sample means, and place that value into my distribution of differences between means. Of course, we're not actually going to calculate the distribution of differences between means. We don't actually literally construct it, just like we never constructed the distribution of means itself. But we do need to know that this is the appropriate comparison distribution for hypothesis testing. And remember, in step 2 of hypothesis testing, you need to determine the characteristics of the comparison distribution. So in this case, we're determining the characteristics of the distribution of differences between means. Based on our null hypothesis that there's no difference between means, the mean of this comparison distribution is 0. What about the variance? And then more importantly than the variance, we need the standard error of this comparison distribution, which is, in other words, the standard deviation of the comparison distribution. So let's talk about how you calculate the standard error for independent samples tests. So remember, for this test, we have two different samples, and each sample represents a population. And our goal is to test for a difference between these two population means, using what we know or what we learn from our sample means. And we're going to make an important assumption for this test. The populations themselves have equal variances, and there's a name for that assumption. It is the assumption of homogeneity of variance. However, it is unlikely that our two randomly generated samples will have the exact same variance in practice. So the samples themselves won't have equal variances. So when we estimate population variance, it's going to take an extra step. So to satisfy the assumption of homogeneity of variance, we compute an average of the two estimated population variances, and we call that a pooled estimate, or S squared pooled. This is the estimated variance for the populations that comes from or draws on information from the estimate from sample 1 and the estimate from sample 2. And we'll use this value, S squared pooled, in further calculations towards the standard error. However, sample sizes may not be the same either. So we know that larger samples will lead to better or more precise estimates for the population variance. And that's because they're drawn from more information, or they're based on more information. So when we calculate that pooled variance term, we don't just calculate a straight average. We calculate what's called a weighted average, which gives the larger sample size more weight in the equation. So if one of your groups has more people in it, then we assume they have the best guess for what the true population variance is, and we'll weight that group higher when we calculate the pooled estimate. So step 1 of calculating the standard error is going to be to first get an estimate of population variance from each group. So we'll ask group 1 and ask group 2, what do you think this true population variance is, essentially, right? So we know that we use the formula SS, or sum of squares, over degrees of freedom to get a population variance estimate. So sum of squares over degrees of freedom for each group will give us that group's estimate for what the true population variance is. Then we can calculate the pooled estimate, or the average estimate for population variance. And remember, this is to meet the assumption of homogeneity of variance. I got 2 different estimates, one from group 1, one from group 2, but I know that in the real world, homogeneity of variance says that there's only one real, true variance for those populations. So I'll take an average of the estimates. But I use a weighted average formula to make sure that a group with a larger sample size has a little bit more influence on what we determine is the true value for population variance. You see a new term here that's introduced, and that is DF total. DF total, or degrees of freedom total, is equal to the degrees of freedom for group 1 and the degrees of freedom for group 2, where degrees of freedom for each group is n minus 1. Step 3 for deriving the standard error for an independent samples t-test is then to find the variance of the distribution of means from each population. So again, we're going to do this twice, one for each population. And remember, here we're using the same formula that you've seen before. It's S squared sub m, the variance of the distribution of means, is equal to S squared over n, or the population variance that's estimated over sample size. So we just calculated the pooled estimate for population variance, and we divide that by sample size for each group to get the estimated variance of the distribution of means for population 1 and population 2, respectively. And note that we calculate these separately, even though the pooled variance is the same, because the 2 groups might have different sample sizes, so the denominator here might change. Deriving the standard error, step 4. In this step, we find the variance for the comparison distribution, which is the distribution of differences between means. So I'm calling this S squared difference, or sometimes I use shorthand and just call it S squared diff. This is the comparison distribution, the distribution of differences between means. And when we build this theoretical distribution, we get some variance from the distribution of means from population 1, and we also get a little bit of variance from the distribution of means for population 2. So we're getting a little bit of variance from both of the sampling distributions. So the variance formula for the distribution of differences between means is just the sum of the variances of the distributions of means. So you just calculated the variance of the distribution of means for population 1 and population 2, and you add those together here in step 4 to get the variance of the distribution of differences between means. And then finally, if that is the variance of our comparison distribution, and what we really need is the standard deviation of the comparison distribution, we know that we can always take the square root of variance to get standard deviation. So the square root of S squared difference will get us S difference, or the standard deviation of the comparison distribution, which we know is also called the standard error. So just a summary of the steps here, I have on a single slide with the formulas. So you could pause it here, take some notes, or make sure that you have those down. And again, another page that you could just pause for terminology, make sure that we are keeping all these things separate. So we now have a bunch of new terminology and symbols. And finally, the test statistic for the independent samples t-test I want to show you here. The test statistic for the independent samples test is M1 minus M2 over the standard error. So the difference between our sample means over the standard deviation of the comparison distribution, which is the distribution of differences between means. So we want to know how the difference between our sample means compares to a distribution of possible differences between sample means. That's the end of this video, and if you go onto Canvas, you'll see that I've also posted a demonstration where I actually work through a problem, calculating the standard error and completing all the steps of hypothesis testing for an independent samples t-test.